A lot of people think that the common base amplifier is more difficult than the common collector and the common emitter configurations. But in this video, I'm going to show you that it's actually just as simple as the others. We're going to calculate the gain, the input impedance, the output impedance, and then we're going to work some practical examples, all involving the common base configuration. Let's go ahead and get started. Now, obviously, this is not a common base configuration right here. This is a common emitter configuration. The common base configuration basically involves taking the source and moving it over to the emitter side. The signal then is injected into the emitter and passes to the load through the collector of the transistor. In a common emitter configuration, the signal starts at the base and is pretty much just replicated at the emitter, but here in the common base configuration, we're just injecting the signal right at the emitter. So you might be wondering, why would you want to do that? What's the advantage? Isn't it just like the common emitter configuration, but without the benefits of the high input impedance? That's what we're going to look at here with this example. If we merely take the source and instead of putting it here at the base, we put it over here at the emitter, we wind up with what I call a bad common base design. In a moment, I'll show how we can make it not bad, but let's start off by listing all of the reasons why this is a bad design. As I just pointed out, putting the signal over at the emitter side of the transistor makes this particular configuration very similar to the common emitter, but without a high input impedance. Secondly, in a common emitter configuration, we typically add a capacitor here to bypass the emitter resistor in order to increase the gain. The gain can then be controlled by the little resistor down here. However, if we put this capacitor in and bypass RE in a common base design, then it's shunting out our source. We're not going to be able to do that. What is the input impedance of our common base configuration here? Well, if we assume an emitter resistance, little r sub e, and then we use impedance reflection to bring these two resistors at the base over to the emitter side by dividing them by beta, then we'll end up with an input impedance of r sub e in parallel with little r sub e, which is in series with the resistors attached to the base divided by beta. Now, clearly, this is not a very big input impedance. If it had been a common emitter configuration, then the input impedance would have been something like R1 in parallel with R2. This is a lot smaller because RE, just on its own, tends to be a smaller resistor than either R1 or R2, and here it's in parallel with something else. Before continuing, though, I'm going to show you how we can convert this bad common base design into a standard common base design, which for a lot of applications is still bad, but it is useful for certain things. Here's what we typically do. We add a capacitor here, and it's a large capacitor that effectively grounds the base for AC signals. When we ground the base like that for AC signals, we wind up with a new input impedance that's just R sub E in parallel with little r sub e. Applying impedance reflection to an AC ground just results in an AC ground. Since little r sub e tends to be a small number, we can usually approximate the entire input impedance as just r sub e. The conclusion is there's no two ways about it. The input impedance for a common base configuration is super small. Now, there are some situations where that could be turned into an advantage. For example, if you have a source that has a very small source impedance and you want good power transfer into the amplifier, then it's good for the amplifier to also have a small input impedance. That's a situation in which a common base amplifier would make a lot of sense. The output impedance of a common base amplifier is nearly R sub C, so it's no different than it would have been in a common emitter configuration. So, all things told, is there really any advantage to the common base amplifier? Well, indeed there is, but it involves an understanding of how the amplifier behaves at high frequencies. The common base configuration works better at high frequencies than the common emitter configuration. And we're going to talk about that in the next video. For the rest of this video, I'm going to derive exact expressions, or at least reasonably accurate expressions, for the gain. Now, you might recall that the common emitter configuration is an inverting amplifier, but how about the common base configuration? Actually, it's not inverting, but at first glance, you might think that it's inverting. Let me show you why. Imagine that you have a sine wave here at the input. The voltage rises a little bit and then it falls a little bit. That's going to go through the capacitor, assuming the capacitor is large enough, and wind up right here at our emitter. At this portion of our signal, the voltage at the emitter is going to be a little bit higher, isn't it? So let's keep track of it. As the source voltage rises up, then the voltage at the emitter rises up with it. As the voltage at the emitter rises up, what happens to the current down through the emitter resistance? Due to Ohm's law, that emitter current is going to rise up as well. When the emitter current here increases, the current up here at the collector is going to increase as well. What's our voltage here at the collector going to be? Well, the collector voltage is the power supply voltage minus the collector current times R sub C. So because of the minus sign in front of the emitter current, we expect the collector voltage to fall. Isn't it then inverting, because that would cause the load voltage to fall as well? The source voltage went up and the load voltage went down, so it seems to be inverting. But what I just said was wrong. Can you find the flaw in my logic? Well, in fact, everything beyond this point is wrong. Here's why it's wrong. Although the voltage rises here at the emitter along with the source, I was somehow assuming that all of the current I sub E necessary to sustain that rise in voltage was being supplied by my transistor. But that logic is flawed because it neglects the current coming from the source itself. It turns out here that the extra current needed to produce that voltage rise that flows down through the emitter resistor is coming from the source and not from the transistor. It turns out then that this particular type of amplifier is a non-inverting amplifier. Here's how I'm going to explain it in a more reasonable way. Let's remove some of these details on the drawing and focus in on the base emitter voltage. I also want to label here the current going down through that transistor. I'm going to label it I. And I want to make a little graph of what happens to that current I as we change the voltage across the base emitter junction. You might remember that that's a p-n junction, so it's just a diode. If the base emitter voltage drop is too low, then no current will flow through the transistor, but once we hit the threshold value, which is about 0.7 volts, then we have a huge amount of current flowing through the transistor. Let's say that we start at a particular operating point on our curve. Let's say that then I reduce the voltage across the base emitter junction. That means that we're going to move leftwards on the graph. What's happened to our current I? Well, I has subsequently decreased. In other words, as the base emitter voltage VBE goes down, the current through the transistor also goes down. I is reduced. If I is reduced, then the current up here at the collector is reduced as well. And everything that I wrote just here in green that I crossed out is flipped to what I expected before. With a reduced current flowing through the transistor, then the voltage at the collector increases. Now look back at the input side and tell me, when I rise to a higher level here on my green curve, did the base emitter voltage increase or decrease? Well, since at the base side we have an AC ground, when I rise here, I squeeze the junction a little bit, don't I? The base emitter voltage decreases rather than increases. We can therefore conclude that as the source voltage increases, then the base emitter voltage decreases, ultimately causing our collector voltage and our output voltage to increase, and I can conclude that it's a non-inverting amplifier. In the next slide, let's go ahead and derive it and figure out what all these voltages actually are from the perspective of the AC signal. You can see that in this drawing, we still have that capacitor attached here to the base that provides an AC ground. Let's draw the AC equivalent circuit at this point to see what it would look like if you were the AC signal traveling through the circuit. We'll start at the source, so I'm still going to have my AC source V sub S. The signal then passes through resistor R sub S, and the capacitor appears as a short circuit from the perspective of the AC signal. We then have our emitter resistance R sub E, and our little emitter resistance little r sub E inside to the transistor. The base is grounded, and it's grounded only for AC signals. The job of our transistor is to multiply the base current times beta and pull it down through the collector. I sub B is the current that flows through the base of the transistor. Attached to the collector, we have two resistors, R sub C and R sub L. I'm interested here in determining what our load voltage is relative to the source voltage. This derivation is relatively easy, rather to the previous cases of the last two videos of the common collector and common emitter configurations because of this ground here that sits in the middle of the circuit diagram. The first thing I'm going to do is simplify our source a little bit by finding the Thevenin equivalent voltage and the Thevenin equivalent resistance. In order to do that, we can just imagine that we have an open circuit right here where I'm drawing the green arrows and find the voltage at that point. It's a simple voltage divider. In order to find the Thevenin equivalent resistance, all I need to do is just ground the source. The two resistors are just in parallel. Let's now redraw it, but I kind of want to make it so that our signal flows from left to right. So I'm going to unwind it just a little bit when I redraw it. Let's put the signal over here on the left. So we now have our Thevenin equivalent voltage source and our Thevenin equivalent resistance. We then have resistor R sub E going to ground. What's the current flowing through resistor R sub E? Well, it's just beta plus 1 times the base current. Let's now draw the upper part of our circuit. Our current source, beta IB, is just connected to ground, and then the other side of it is connected to two resistors in parallel. Let's apply Ohm's law to this circuit here on the right. V equals IR. Therefore, the load voltage is just beta IB times the resistance. Let's now apply Ohm's law to this little circuit on the left side as well. V equals IR. There's V, there's I, and here's the net resistance of this circuit. We're going to need to know what the base current IB is, so let's go up here to this equation and solve for I sub B. Let's now substitute the base current into this equation. I basically now have my Thevenin voltage in terms of the load voltage, but what I want is the load voltage in terms of the Thevenin voltage, so I'm going to move the load voltage over here to the left. So what was in the denominator is now in the numerator, and what was in the numerator is now in the denominator. I have the load voltage in terms of the Thevenin voltage, but what I really want is the load voltage in terms of the source voltage, so let's substitute in for our Thevenin equivalent voltage. I'm now going to move beta over beta plus 1 into the numerator, leave RC in parallel with RL alone, and I'm going to substitute in for my Thevenin equivalent resistance. Let's now write everything out, but I'm going to simplify by assuming that beta is large enough that beta over beta plus 1 is nearly equal to 1, so we can just ignore it. Well, we basically have an input divider, and then we have a gain segment. The gain segment of a common base amplifier is basically the resistance seen from the collector divided by the resistance seen from the emitter. In that sense, it's very similar to what you have in a common emitter configuration, except that it's non-inverting. This expression for the gain is entirely correct, but there are easier ways to find it. Now let's try to find it by inspection using two different methods. In the first method, we're going to be using a full and correct expression for the input impedance, but then I'm going to have to truncate the gain. In the last example, I found that the gain was the collector resistance divided by the emitter resistance. But in option 1, I'm going to only use the emitter resistance looking up through the emitter in order to find the expression for the gain. It turns out that that's correct. For option 2, we're going to include the full emitter resistance when we calculate the gain, but then we're going to use a truncated expression for our input impedance. That's basically what we got when we did the full derivation. Let's go ahead and get started here with the derivation. It turns out that it's relatively easy. The full and correct expression for the input impedance of this particular circuit is the emitter resistance R sub E, which is in parallel with the little r sub E, which is connected to a ground. An AC ground, anyway. The output impedance is just R sub C. We're going to neglect the output impedance of the transistor itself since it tends to be pretty large. I should point out that the input impedance for the circuit here on the right is exactly the same as the input impedance for the circuit on the left. We're just going to use a different method to calculate the gain, but that doesn't change the fact that the input and output impedances have to be the same. The gain of an amplifier is given by three different components: an input voltage divider, a gain segment, and an output voltage divider. For our gain segment, I'm going to include the resistor attached to the collector and divide it by the single resistor that's attached to the emitter, and I'm not going to include RE and R sub S. Those are included over at the input impedance side, and if I were to put it in both places, it would somehow be double counting. This is the true and accurate voltage at the emitter that gets multiplied by our gain segment here. I like option 1 a little bit better for that reason. Our full expression for the gain then has our input voltage divider, our gain section, and then finally our output voltage divider. Let's move on to option 2. So for option 2, we have our signal and our resistor R sub S. But then I'm going to truncate the input impedance and not include it here. I'm just going to include R sub E. However, then for my gain, I'm going to include everything attached to the emitter. Here for our gain segment, we have the resistor up here at the collector. But then for the emitter, I'm going to include everything. I'm going to include little r sub E, which is in series with R sub E and R sub S. Our output impedance is still R sub C, and our load impedance is R sub L. For our full expression for the gain, we have a voltage divider. Let me call this voltage here V1, and it shows up over here as well. V1 is not the true voltage at the emitter. Although our expression for the gain is going to be just what it was with option 1, you have to be mindful that the voltage here, V sub 1, is not a true voltage that really appears anywhere in the circuit. We then have our gain segment, and then we have our output voltage divider. It's also worth pointing out that what we have here in blue is just RC in parallel with R sub L, and that's the expression that we found when we did the derivation from the small signal model. It might not be immediately obvious if you look at the expressions from option 1 and from option 2 that they're the same, but if you do a little bit of algebra, you can find out that these expressions are entirely identical to one another. Personally, I like option 1 better because you're using the correct expression for the input impedance. You just have to remember that for the common base amplifier, you don't divide by the full emitter resistance, but only little r sub E right here. Let's work a few examples together so we can get some practice. In example 1, we're going to be finding the input impedance, the output impedance, and the gain. I'm going to be assuming high frequencies here so we don't have to get sidetracked with the values of the capacitors. We're just going to assume that these 3 1 microfarad capacitors are large. Look at that low impedance source. The source resistance here is only 10 ohms. That's a use case for the common base amplifier, by the way. Let's do a DC analysis to make sure that the transistor is in the forward active mode. If it's cut off or if it's in saturation, the amplifier is not going to work at all. The base voltage is going to be some fraction of the 10-volt power supply. In this case, that fraction works out to be 1/5. We wind up with 2 volts as the base voltage. You might be thinking, well, that seems a little bit small. But in fact, if you're building an amplifier with a reasonably high gain, you want the small signal to be down where the voltages are low. And what you want, in addition to that, is where the signals are amplified, you have a lot of room to swing around. So in order to make sure that the transistor doesn't saturate when the collector swings low, you want the voltage here at the collector to be somewhere midway between the power supply and ground. You don't want this voltage to be too low. You want the low voltages down here. That's what we've arranged. Assuming we have a forward bias diode, then we should have about 0.7 volts drop down to the emitter. so the DC emitter voltage should be roughly 1.3 volts. The DC emitter current is going to be 1.3 volts divided by 1 kiloohm, giving me 1.3 milliamps. The DC collector voltage is going to be 10 minus 1.5 kiloohms times the 1.3 milliamps. That gives us 8.05 volts. The voltages are nicely arranged, high, medium, and low, so I can safely conclude that this transistor is biased in the forward active region. Little r sub e, which is important for AC analysis, at room temperature is just 26 divided by our emitter current expressed in milliamps. In this case, that's 20 ohms. Let's now find expressions for the input and the output impedance. Well, the input impedance, if I want the full and true expression for it, is going to be 1 kiloohm, and that's in parallel with R sub E, which leads to a ground. It's only 19.6 ohms. That's a really small input impedance, isn't it? But luckily, our source is a 10 ohm source. Therefore, these are reasonably well matched. How about our output impedance? Well, output impedances are pretty easy to calculate. It's just going to be somewhere near 1.5 kiloohms. We're now ready to draw our equivalent circuit and calculate the gain. We have our source voltage V sub S, a source impedance of 10 ohms, and then our input impedance of 19.6 ohms. This gives me the AC voltage at the emitter through that voltage divider. Now for the gain. Let's clean up our circuit drawing just a little bit here. The expression for gain of a common base configuration is the resistance at the collector, that's the numerator, divided by this resistance looking up the emitter, that's the denominator. That's 1500 ohms divided by 20 ohms. Now for our output voltage divider, we have an output impedance of 1.5 kiloohms and a load of 500 ohms. I can now find my gain by inspection. There's the input part, here's the gain part, and finally we have the output part. These numbers work out to 0.662, 75, and 0.25. Basically, you can say that the gain of this common base amplifier is pretty high, but it's moderated by the input and output impedances a little bit. We wind up with an overall gain of 12.4. In example 2, we're going to turn our attention to the capacitors because we ignored them in example 1. Would the capacitors work for radio frequencies? How about audio frequencies? At first glance, I can kind of recognize this at the output side as being a high-pass filter. What's the corner frequency of that filter? Well, if you watch my video on one-pole filters, then you would recall that the corner frequency is very nearly 1 divided by 2 pi RC. In this case, R is 500 ohms, and the capacitor is 1 microfarad, or 1 times 10 to minus 6. We wind up with 318 hertz. So, yes, it would certainly work for radio frequencies because those are going to be passed by the high-pass filter. For audio frequencies, we're going to have a bit of a problem. For high audio frequencies, they'll make it through, but for the low audio frequencies, they won't. And 318 hertz, if you're familiar with a piano keyboard, that's somewhere near the middle. So that's kind of right in the middle of the frequencies that we're used to in everyday life. So it's not going to work at audio frequencies. If we look here at our input impedance side, we also see a 1 microfarad capacitor, and then we effectively have the rest of our input impedance. The input impedance for this circuit was calculated to be 19.6 ohms. We again have a high-pass filter. Let's find its corner frequency. In this case, it's 8.1 kilohertz. It's a high-pass filter, so radio waves will go right through that capacitor, but this is pretty much just going to block all of the audio frequencies, which usually lie in the hundreds of hertz or so. I now want to make a small note, even though the example has pretty much been worked. If you use impedance reflection to reflect the base impedances over to the emitter side, then we typically need to divide by beta, or beta plus 1. What do we have attached to the base of our transistor? Well, we have two resistors. We have a 20 kiloohm in parallel with a 5 kiloohm, and then we have a 1 microfarad capacitor. Instead of writing 1 microfarad, I'm going to write down the impedance, 1 divided by j omega c. When we use impedance reflection, in order to move those impedances from the base side to the emitter side, we have to divide by beta, don't we? So how are they going to change? Well, the capacitor's impedance is also going to get divided by beta along with the other two resistors. If we continue here on our emitter side, we have little r sub e, a 1 kiloohm resistor that was used for biasing purposes, and then we have a 1 microfarad capacitor. This gives me my input impedance. My goal here is to see whether or not this capacitor attached to the base would somehow limit the operation of this amplifier at high frequencies. But you see, it's a little bit difficult now because our input impedance now has 2 poles rather than just 1 pole. Notice, however, that beta is sitting down here next to C. So the capacitance kind of gets multiplied by beta when the transistor is in this configuration. So for the purposes of the input impedance and the limitations on frequency, this 1 microfarad capacitor kind of behaves like a 100 microfarad capacitor. What this means is that it's entirely reasonable when I calculate my corner frequency to just treat that capacitor at the base like an AC ground. But you see, problems can occur if the capacitor attached to the base is too small. If I kind of make a plot of my gain versus my operating frequency and the base capacitor is too small, then I'll get a curve that looks something like this. This high-pass filter that has a very low corner frequency is due to the emitter capacitor. That's this one. This high-pass filter with a higher corner frequency would be due to my base capacitor if it were too small. That's not the case in this circuit, but in the next example, we're going to look at what happens if you don't have that base capacitor there. You'll end up with a reduced gain. Everything in this example is identical to examples 1 and 2, except that we don't have the base capacitor attached. Let's see what happens to the gain. We've already calculated most of what we need. The little emitter resistance R sub E was 20 ohms. Let's find an expression for the gain. We're going to first have an input voltage divider. Our input impedance is going to be 1 kiloohm in parallel with RE, which is in series with our impedance that's reflected from the base side. That's 20 kiloohms in parallel with 5 kiloohms, and we need to divide that by beta, which we can approximate as 100. We have a voltage divider set up by the source resistance, and I'm going to write down my input impedance again. Now for our gain segment, I need to include in my numerator the resistance attached to the collector, 1.5 kiloohms, and in the denominator, I need to include the resistors looking up the transistor. In this problem, that's little r sub E plus my base resistances reflected over to the emitter. And then we have our output voltage divider, a 500 ohm load, a collector resistor of 1500 ohms, and this works out to 5.3. If we go back to the previous problem, our gain with that base capacitor attached was 12.4. The reduced gain is due entirely to the presence of that base capacitor, and that's why we put it there. It makes a better amplifier. Now, incidentally, when I calculated the gain, I used the full and correct value for the input impedance, but I truncated the gain for the resistors attached to the emitter. I only used the resistors to the left of this black line. But as you recall, there are 2 options for finding an expression for the gain. And just for completeness, I want to show what the expression for the gain would have been had I used option 2 instead of option 1. For option 2, I'm going to truncate my input impedance. I'm not going to care about the transistor at all for the purposes of calculating the input impedance. So this divider is going to be a little bit simpler. I'm just going to have 1K making a voltage divider with the 10 ohm source impedance. Now in my expression for the gain, I can use all of the resistors attached to the collector. That's 1500 ohms from R sub C up here, and it's attached to the load resistor, which is 500 ohms. And then in the denominator, I'm going to include all of the resistors attached to the emitter, including those reflected from the base. From impedance reflection, we have 20 kiloohms in parallel with 5 kiloohms, and then reflected by beta over to the emitter. Those are in series with my emitter resistor R sub E, which is then in series with a 1 kilo ohm resistor and a 10 ohm resistor. When you calculate it all out, these two methods gave exactly the same answer. In summary, in this video, we basically found out that the gain of a common base amplifier, which is non-inverting, is just the resistors attached to the collector divided by the resistors attached to the emitter. And in that sense, it's very similar to the common emitter amplifier, which has the same gain except that it's inverting. So in that situation, why would anybody ever bother to use the common base amplifier given that it has worse input impedances relative to the common emitter amplifier? That's actually going to be the subject of the next video. We're going to look at the Miller effect. It turns out that the common emitter configuration doesn't work as well at high frequencies as the common base amplifier. That motivates us in certain circumstances to actually use the common base amplifier.